Uh-oh. Let's see. Sorry, are we recording? Oh, I think we're recording. Sorry about that. Okay. It's just me, Mr. Wee. Let me just continue with the last few notes. So the last thing that we're going to talk about is numerical derivatives. Go ahead and copy this down. And they're called symmetric differences. And copy down all the notes. So I'm going to go through this. Previously, we learned about how to take the derivative with a difference quotient, an approximation. This is what it looks like. That's what I mean by a difference quotient. This is a quotient, okay, like a fraction, and then the difference is f of x plus h minus f of x, right? This one is called a symmetric difference, symmetric. So I said, however, we may also take an approximate derivative with a symmetric difference. So before you learn a difference quotient, being that x plus h is inherently farther away, like if you had a point of x plus h is like here, right? And to take that derivative, you take sort of like you take like a slope between the two, but as the h gap gets closer and closer to 0, okay? That's what we had here. This is a little bit different. We may also take an approximate derivative with a symmetric difference, and what the quotient would look like would be f of x plus h. I know it's kind of hard to read. F of x plus h minus f of x minus h. So what that would look like is this. I know it's a little hard to see, but you have an x point here, right? And what you do is you subtract h, so that's x minus h, and over here you have x plus h. And what you do is you take these two points, and then you take the difference between the two, you take the slope between these 2 points, and as h approaches 0 from here and here. Well, the reason why we call that symmetric is because the gap is not only h length away, but it's 2 h's, this h and this h. So that's why it's denoted by f of x plus h minus f of x minus h. So now we're just taking, so I know it's hard to see, but let me see if I can kind of zoom in here. Again, what I had up here was the distance from x to x plus h, and then we'd make that gap of h approach 0. This is a little bit different in that you have an x and x plus h, and then x minus h. You take the distance between these two, you take the slope between these two, f of x plus h minus f of x minus h, and then not only are you h length away, but you're also h length away and another h, that's 2 h's away, okay? So let's kind of, and go ahead and write this down. This computes a slope, this computes slope between 2 nearby points, so x minus h and x plus h, on opposite sides of x. So we'll call that x, sorry. Far away from x, and away, no, not far, but and away from x, okay? And I also says a bullet point, this application is used by a calculator. So again, numerical derivative of f at x would be f of x plus h. So this is how you're, so this is an example here. Let's say that h was equal to 0.01, like some small distance, and then this, it would be plus h minus h, and then on the bottom would be 2 times h, would be 2 times 0.001, okay? In your calculator, this is denoted as nDeriv, basically, of f of x, and then you're going to put the variable that you're using, which is x. So I know that's hard to read, this last bullet point. Our calculator, it looks like this. Lowercase n, capital case D for derivative, nDeriv, and then it's going to say dot, dot, dot. So I actually have the calculator here. So basically, if you use this function, it does not use f of x plus h minus f of x. It will actually compute something like this. It will compute a symmetric difference. So it'll take f of x plus h minus f of x minus h, meaning it'll attribute some kind of small value, be like 0.001, and it'll add it to the x, and it'll subtract it from the x and divide it by 2 times that gap, okay? So on here, let's take a look here. If I remember correctly, I believe it's under math. Yep, under math, it's nDeriv. You press that. Oh, this one's actually really nice. So let's look at how it looks. So on the TI-83, it looked like the way I showed you, but kind of show you here. So what you're doing is you're taking the derivative, okay, at, I don't know, like of some kind of, so actually just write this down here, okay? So here's an example problem. F of x equals x to the third power. Use a numerical derivative to approximate, let me expand this out a little bit. To approximate f of 2, so that says f prime of 2, the derivative of 2. So I said the derivative of x equals 2. And I won't give you a problem like this on the exam, but it's actually really good for a lot of your questions on the homework. And it's just a good tool in general. But here's how it would actually look. Here you have df over dx. So another way of saying f prime is just saying the derivative of x with respect to x. And in this case, in your calculator, you're going to put d over dx of x over 3. And it's going to have this weird line here. And it's going to specify at what point are you talking about. Well, we said at x equals 2. Derivative x equals 2. What that might look like on the older calculators is you put nDeriv, you put the function x to the third power, comma, and then you put 2. Or I think you put, more appropriately, you say x to the third power, you specify what variable it is, x, and then you have to say at what point x equals 2. So that might be on the really old ones in the TI-83s. And then this is the math it'll do. It'll take your x value, so take your x value, add an h, and then this is your x value minus an h. And it'll give you a random, or it'll attribute h as something like very small, like 0.0001. Remember, h approaches 0, so they give you a very, very, very small value of h. And then in the end, they'll give you an approximate derivative. So this would be 12.0001, but to be honest, we just round that to 12. So on your graphing calculator, so the new ones, the 84s, you'll say x is derivative of d to the x. It would be the derivative of technically whatever's in this box, which is x caret 3. I'm going to move out. And then follow my mouse here. So what this is the derivative of x to the third power, and then you go back to the bottom, the denominator says with respect to x. And then you say at which value x equals 2, and you just press enter. See, 12.001. Okay, this is what 3.2 kind of discusses in your lesson, but it's a little hard to understand maybe. Okay, and that's pretty much it. I mean, I gave you some more directions here about what you should look like. So this is actually number, so when I say go to math and go to number 8, let's show that one more time. So in order to do that, I go to math, and then it's actually the 8th option in the first tab or screen. So you can scroll down to it, or it's just the number 8, so you just press 8. There you go, and you have the option again, okay? So this is kind of a note to myself saying that these are the questions you guys can try in class, but we didn't have time to try this in class. This is pretty much number 17 through 25 in 3.2, page 116. Okay. Warning though, write this to yourself. Right. Warning, page 114, example 3. This method is inaccurate at times. So, like, let's just say if you plugged in, if you plug into the function here instead of x to the third power, you put in the absolute value of x. The absolute value of x should have a corner. This is what it normally should have. So I know it's hard to see, but I'm going to draw it in purple. This is the y-axis. This is the x-axis. And the actual graph is this sort of really, really sharp V. And you know at x equals 0, there is no derivative. At x equals 0, there is no derivative. Okay? But however, this method that I showed you, since it's adding h and it's subtracting h, the math here actually works out. It's mainly because of here with the 2 times the h. This method, since you're adding actual values that don't approach 0, and remember I said they're approximations, it will actually give you a real number at, like if you actually said ender absolute value comma x comma 0, let me fix that really quick. So if you put ender x comma 0, or you put this here in your calculator, d of dx of absolute value of x equals 0 here, then it would actually give you a value of 0, which is not true. It should be, your calculator should say error, but it doesn't. It actually gives it a real slope value of 0. So just be very careful. You cannot rely on this all the time. It's mainly to do with this here. It will just calculate and compute that it does have an actual difference between, because you're not finding the difference between here and here, you're finding the difference between these two that will actually end up giving you a real number. So just be very careful with this technique. That's all I have for you guys, and that's pretty much it for this week. Now tune in for next week, and then we will continue our notes, and then you guys can study for your exam. Thank you guys. You guys have a great day. Bye.